La, la, la. Very good. Let us begin with a word of prayer. I'll start. Dearly Father, we thank you for this day again, Lord. I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So I posted a supplement from a calculus book we were using here before, Salas, Hilly, and Etjen. This is a 10th edition. And so I'm going to try to kind of work my way through the first part of their chapter 11 for us to have a good treatment of sequences. The math faculty love this book. I mean, it's a very, very good book. You might wonder why we stopped using it as the calculus book. The answer is that it was $370 in the bookstore, which was a bit much. So, how much is your book right now? Well, I mean, I didn't require you to get a book, right? So you don't know. But I have posted a PDF of just their chapter 11, right? Now, hopefully, if I have inadvertently posted part of chapter 10, ignore that, obviously. I sent something to the secretary this morning, and I have some of chapter 10, so I'm not sure if I also posted that. I haven't had a chance to look at Blackboard yet, but if there's part of chapter 10, ignore it, right? Chapter 11 is on sequences, so let's look at that. So section 11.1, they start by talking about the least upper bound axiom. What's that? So let me tell you what we're doing. We are going to take a look at some deeper properties of real numbers so that we'll have a thorough and complete, hopefully a thorough and complete understanding of both sequences and their limits, all right? But really, it strikes at the heart of what are real numbers, all right? So one of the things that makes real numbers real is the least upper bound axiom, all right? So we talked about this before, but if S is a subset of the reals, then if, there exists M in the reals such that X is less than or equal to M for all X in S, then S is bounded above. Sorry, this means there exists, okay? This, if you're wondering, means such that. So if we had a set of real numbers, we could talk about whether or not it's bounded above. If you could find a number that's bigger than the whole set, right? That would be bounded above. Likewise, if there exists, let's say, little m in R such that X is greater than or equal to little m for all X in S, then S is bounded below. Okay? All right, so just to be a little bit more precise here, example, if we had S was equal to, say, the closed interval from 0 to pi, where pi is included, what would be some upper bound? What would be an upper bound? So guys, could you tell me what would be an example of an upper bound for this set? Don't all speak at once. Anything over the pi. So like here? No, I mean, okay, so how about 4? Would 4 work? 4 would be an upper bound, right? What would be a lower bound here? How about like -1, right? This could be a possible m, right? This could be a possible big M. So you can also talk about the least upper bound or the greatest lower bound. What's the least? It's just what it sounds like, right? Least upper bound for S is the upper bound of S which is smaller than all other. Well, it's smaller than any upper bound of S, right? In other words, the least upper bound, or lub, of S is less than or equal to m for all upper bounds m of S. So for my silly example, what's the least upper bound of the lub of 0 pi is what? Yeah? Pi, yes, yes. It does not have to be complicated, right, folks? Just that, just language. It's pi. And in this case, if the least upper bound, all right, if the least upper bound is also an element of the set you're talking about, it's called the maximum of the set. So in this case, you could also say that that's equal to the max of 0 to pi, okay? Now, there's also a greatest lower bound. Guess what that means? The greatest lower bound, or glub of S, is greater than or equal to m for any lower bound m of S, right? So what's the glub of 0 to pi? What's the greatest lower bound of 0 to pi? I heard a 0. Do you guys agree? I think I agree. Now, just to bring, if the greatest lower bound is also in the set in question, it's called the minimum. In this case, there is no minimum for this set. So this is not equal to the minimum. So minimum would suppose that there is actually an element inside the set 0 to pi, which is smaller than every other element, right? No matter what you pick in the interval from 0 to pi, I always can take it and divide by 2 and find something smaller. It's impossible to find a smallest element of 0 to pi with the standard ordering of the reals. All right? Okay. So what's this least upper bound axiom? Here's the least upper bound axiom. As he says, axiom 11.1.1 on page 529 of Salas-Hilly handout. He says, every non-empty set of real numbers has that's not hashtag. No hashtags in here. Hashtag, no hashtags. Has a least upper bound. All right. And that brings us to the following theorem. If M, oh, I have messed it up. Good grief. There is a kind of important sentence in between those two sentences that's here that I didn't write on the board. And, you know, take this, for example. Why is what I have on the board nonsense? How about this? Is that a non-empty subset of real numbers? It is. Yeah, sure. Does it have a least upper bound? No, it doesn't even have an upper bound. All right? So here's the statement that I should have written. Every non-empty subset of real numbers, this is important caveat, that is what? That is bounded above. Has a least upper bound. So if there exists one upper bound for the set, there has to exist a least upper bound. That's the axiom. Okay? That's important because otherwise, you know, we get into trouble with stuff like this. All right? So here's the theorem. Theorem. If M has a least upper bound, has least upper bound of set of S, which is a subset of the reals, all right, and epsilon is a positive number, then there is at least one number S in S, little s in big S, such that M, I said has, but what word was I supposed to write there? Is, yes. That's definitely an is. Right? M is, right? Otherwise it wouldn't make sense. If M is the least upper bound of S, all right, and epsilon's a positive number, then there's at least one number S in S such that M minus epsilon is less than S and is greater than or equal to M. All right, let's try to think through this. Yep. What is this? Oh, this means that, sorry, this means S is a subset of the real numbers. Mm-hmm. Good question. All right, so here's the proof of this theorem. He says, let epsilon be greater than 0. He says, since M is upper bound, right? What's that say? That means that S is less than or equal to M, right? For all let's say for each S in the set S. All right? So he says, all we have to show is that there's some number S such that m minus epsilon is less than S. Maybe it's helpful to draw a picture of what we're trying to do for a second here. So, I've been drawing, so maybe this is a picture of the set S. S doesn't have to be continuous or like a connected set. It could be a discrete collection of points, right? And yet there is this M that's an upper bound on S, right? And what this theorem is saying is that if M is the upper bound, is the least, not just upper bound, but the least upper bound, then if you look at M minus epsilon, which would be somewhere in here, right? Right, if you look at M minus epsilon, that means that what? There has to be some kind of at least one point, there's at least one element of the set S that's in there somewhere. So that would be M minus epsilon less than S less than or equal to big M. Yep. So how do we argue this? He says, suppose on the contrary. Suppose on the contrary. Suppose otherwise. That there is no such number S in S, then what? If there was not such an S, what would that mean? He said that would mean that X is less than or equal to M minus epsilon for all X in S. What would that mean, though? Does that make sense? I mean, do you understand what I just wrote? So either there is an S somewhere in there, right? In which case the theorem is true, or there's not. If there's not an S in here, what does that say? That says that every point in the set S is less than or equal to M minus epsilon. But what does that make M minus epsilon then? Yeah? It would mean our least upper bound is not really the least upper bound, right? In other words, she's saying that this means that M minus epsilon is an upper bound. Oh man, that's an upper bound for S, but we can't have that, can we? It's an upper bound smaller than what? The least upper bound of S, which we called M, right? Is it clear to you why M minus epsilon is smaller than M? We're taking M and subtracting a positive quantity, right? But is that possible? Can we have a bound smaller than the least upper bound? The answer is, of course, no. This is a what? This is a contradiction. So what I'm exposing you to right now is the method of proof by contradiction, right, which maybe you haven't seen before. I don't know. But this is a standard technique of proof in mathematics. Yeah.
Like, what is the least upper bound? Is it just the max of the min of the set? Is that all it is?
If it's in the set, it's the max or the min. So like if I had the least upper bound of 2 to 3 would be 3. The greatest lower bound of 2 to 3 would be 2. The max of 2, 3, and the min of 2, 3 does not exist as a real number. Max or min means that it's also in the set. You've seen maxes and mins in Calculus 1. We talked about the extreme value theorem, right? If you have a continuous function on a closed interval, the maximum or minimum of the range is attained by that continuous function, right? But that's because of the continuity and the rather special property of a closed interval. Okay, so anyway, this is a little bit picky, but let's go on here. You can also prove, as he does in section 11.1, and I won't do this because it's almost the same thing, that every non-empty subset of real numbers that has a lower bound has a what? If you have a set which is bounded below, guess what? There exists a what? A greatest lower bound, right? And there's also an analog of this theorem that if you looked at, say this was m, right? And if you looked at, say, little m plus epsilon, what would that tell you? There exists at least what? At least one s in S such that what? Little m is less than s, less than or equal to s, and less than m plus epsilon. Because if it were not so, then m plus epsilon would serve as the greatest lower bound, would serve as a lower bound, right, for the set S, which would contradict little m being the greatest lower bound. That would be a bigger, anyway. So there's a corresponding theorem and result for greatest lower bounds, all right? Now, it may not be obvious to you, but this is actually mission critical to what makes calculus work. This is a way of describing, in some sense, the density of real numbers. How real numbers are so close to each other in this sense, and that there's always another real number defined between two real numbers. This is at the heart of what makes calculus work, but it's subtle. All right, and that's why it's an axiom. All right, you can't prove this from more basic things unless you had a really careful definition of real numbers, which then would assume a bunch of math you haven't had yet. So this is what we have to do here, okay? So that brings us to section 11.2, which we already were kind of in last class, all right? So section 11.2, which is sequences of real numbers. But I just, guys, I took a look at my notes, and I'm just not happy with the level of my written course notes. And so I thought it would be helpful and healthy for us to have a supplement from an honest to goodness, really well thought out calculus book. And you can't beat this one for sequences, okay? So what's his definition? We've seen this before, right? Sequence of real numbers is what? Is a real valued function of the set of positive integers which I use n for. So last time I used notation, I said that's like A is a mapping from n to R, a function, right? And, alternatively, we can look at it as what? A1, A2, A3, A4, dot, 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 dot is a sequence, right? We can look at a sequence as a list of numbers. You give me a list, I can give you a function, and vice versa. All right? These are interchangeable ideas. And he brings us to some terminology. He says this guy is the so-called first term in the sequence. All right? What's the second term in the sequence? I'm not even going to write it down. You can tell me, what is it on the board? A2. Yeah. Third term? A3. Now, if you have two sequences, let's say a sub n equals 1 to infinity, and b sub n equals 1 to infinity, we can define a sub n plus b sub n, right? We can add the sequences together. What else could we do? We could take the sum of two sequences and get a sequence. How about we could also look at like constant times a sequence. That would be a new sequence, right? We could multiply two sequences, term by term, a sub n, b sub n. These are all new sequences from old, right? Just like you'd construct new functions from old. How did you construct new functions from old in pre-calculus? Do you remember? You take two functions, f and g. You define f plus g, f times g, like a constant times f. How did you do those things? Pointwise, right? Like f plus g of x is f of x plus g of x. F times g of x was f of x times g of x. All of those rules naturally extend here because sequences are functions. So we can define the addition or the multiplication or the scalar multiplication of a sequence pointwise. It's just that the points we define them at now are just natural numbers. Nothing especially surprising here. He says you can also form reciprocal sequence, quotient sequence. Great. Now, let's move on to something a little bit less kind of, this is just name calling at the moment. Let's move on to something with a little bit more substance to it. It may or may not be the case that you have a formula for a sequence. What's a formula for a sequence? Let me just give you an example of a sequence where we do have a formula. So if a sub n is equal to 2n plus 1 cubed, right? That is a formula, okay? So with that formula, the sequence looks like what? We've got n equals 1 gives me, oh, did I say cubed? I don't want a cube there. That's too much work for me. Square, square, square. Cube I actually have to think about. 2n plus 1 is what? We got what? 3 squared? 5 squared, yeah? 7 squared? 9 squared? And so forth. So that's a sequence, and that's its formula, right? In other words, a formula is when we have some algebraic or perhaps transcendental expression that captures the nth terms in terms of like one familiar rule, right? It may or may not be the case that you can actually see that. So another one would be something like this. A sub n equals 1 to infinity, equal to 1 squared, 3 squared, 5 squared, 7 squared, 9 squared. What would the formula be here? Can you see it? A sub n equals to what? What's that? That was the previous example. It is not the same. This one starts at 3 squared. This one starts at 1 squared. I had a 2n plus 1 again. No, 2n. I heard a 2n minus 1. And that would be right. So 2n minus 1 squared starts at 1, and then it goes, so like 2n minus 1 does what? It goes 1, then 3, then 5, and so forth. Okay? All right, you're going to have to give me a second to think about this one. Hopefully I remember it right. 21, 19, 1, 21, 19, 1, 21, 19, 1, 21, 19, 1, 21, 19, 1. Why aren't you guys following? I mean, by now you should be chanting with me. You're not. What's wrong with you guys? Bunch of communists. Let's see here. What is this sequence? This is my most patriotic example so far. You get it? What is it? 21 equals U? Yeah. 19 equals S? 1 equals A? Yes, very good. So this is the USA. USA. So it's a very patriotic sequence. But you know, sequences don't have to have a formula. They could be derived from something sillier, right? Okay, now finding the formula for a given sequence may or may not even be possible. All right. I was sitting undergraduate at the time, and I lived in Miss Matthews' upstairs of her house. She was 85 or 86, so she wasn't supposed to go upstairs. I think she might have when I wasn't there. But anyway, her son, Dudley, came home. He's like, I was at the bank, and we're trying to figure out what this was, and we didn't know what it was. And I was like, okay, I'm just kind of listening, you know, and fine. And they started listing numbers, 1, 8, 64, 125, and so forth. And they're like, I don't know what that was, but what is it? Cubes, right? Yeah, this is a sub n. I don't know. So it's you know, it's funny. It depends on your experience, right? If you have worked enough with numbers to know, oh, that's wrong, I missed something. So you guys who said cubes, you ignored my mistake. Good for you. 27, 64, 125. Okay, yeah, I kind of missed one, right? So that's 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, right? So this would be a sub n equals to n cubed. Now, I should confess, at the moment, all of my sequences have started with 1. Is this universally assumed? It is not. In fact, truth be told, some honesty, really A such that S goes to the reals where S is a subset of the integers and has property S in S implies S plus 1 is in S, and the minimum of S exists. That's a sequence. I mean, a sequence is really just a function from a set of integers which has a starting point, and then after that point, every single stupid integer past that point, right? Like it could start at -5. You could have a sub -5, a sub -4, a sub -3, a sub -2, a sub -1, a sub 0, a sub 1, a sub 2, a sub 3, a sub, right? I mean, you could start wherever you want is what I'm trying to say, in the most complicated way possible. Yeah.
Wait, can you write down what you just said instead of that?
Sure. This is a sequence. The point is n sub naught could be whatever. N sub naught is the minimum in my more complicated way of saying this. Now, I don't know. In practice, almost always the sequences we look at either start at 1 or 0 or some small positive integer. 2, 3, whatever. You know? Example 7, if you had a sub n is 1 over n minus 7, you know? You probably would want n to start for what? I mean, personally, I want to start at 8. But anyway, a sequence, we should tell you the starting point of the sequence, right? It's not enough just to say the formula, technically speaking. You should also say the starting point. It is assumed that it starts at 1 in here, unless we say otherwise, though, okay? So it still has, like if I say a sub n is n squared, that means we're looking at the sequence 1, 4, 9, 25, okay? All right, enough about that. Way too much about that. Way too much about that, so sorry. Terminology. Increasing. And I'm going to have to differ with the book here, okay, guys? So for me, I guess well, I don't know what to do, guys. This is a problem. I'll just tell you, there's disagreement here about how this should be referred to. And it depends on which book you're looking at. So I'll tell you what it says in Salas and Hilly right now, okay? So he defines increasing, non-decreasing, decreasing, and non-increasing as follows. All right? This is what's in the handout. But in practice, in other courses, and I think often in life, you'll find the following definitions, more typical in my view, would be strictly increasing. This is strictly increasing. All right? This is just increasing. This one is strictly decreasing. And this one is just decreasing. So if you want to read things I've written in any other course, you have to go with what's read. So I propose that we should stick with what's read. All right? That means we're going to have to be disciplined as we read this handout to translate. Right? Is that okay? Yeah. Now, would it be less confusing for you guys if we stuck with what was blue and just stuck with the handout? I mean, we can do that. Take a vote. Democracy, right? Red's a better color. Funny. Let's see here. All right, now, but anyway, more to the point, if your sequence satisfies any of these conditions, right, it's said to be monotonic. Monotonic. All right, I will stick with what's in blue because it's what you have written, and otherwise it's going to create confusion for me as I lecture from here. I'm just warning you, as you go to other classes, you might have the red terminology used, okay? But I will stick with the blue. And if you use the red, because that's how you've been taught before, I'm not going to take off points, okay? So, in as much as it doesn't confuse you. All right, let me stop. All right, so a sequence that satisfies any of these conditions is called monotonic. So an example of a sequence which is not monotonic would be, what's a not monotonic? How about this? 1, minus 1, 1, minus 1. This would be what? A sub n equals minus 1 to the n plus 1? Yeah? So there's a sequence which is not monotonic, but he gives the sequence 1, 1/2, 1, 1/3, 1, 1/4, and so forth and so on, also not monotonic. Right? Yeah, it's got a subsequence, like the 1 over n type terms, that's decreasing, right? Strictly decreasing. But, excuse me. No, it's decreasing. Dang it. All right. Anyway, this is not monotonic. All right. So, listen. So either one of these, what could we capture this as? This is a sub n plus 1 over a sub n what? If it's let's say so star assume positive, all right? If we assume that we're working with a positive sequence, then what? If you solve for an plus 1 over an, what do you get? Is that less than or greater than 1? Maybe I should. Right? It's greater than or equal to 1. If you divide both sides by an, you get 1 is less than or equal to a sub n plus 1 over a sub n. Star, what condition do we got? Again, assume positive. Why am I assuming positive? Otherwise, when I divide by a sub n, I would flip the inequality, right? Assume positive. We have a sub n plus 1 over a sub n less than or equal to 1, right? So we could test whether or not a sequence was, let's say, increasing or decreasing, depending on what? If the quotient of the n plus 1th term in the sequence over the nth term in the sequence was what? Like larger or smaller than 1, right? So sometimes this is like very helpful because it gives you a way to kind of sort through whether or not a sequence is increasing or decreasing in the abstract with a pretty good argument. So he does this for example. His example 2, I think, is actually pretty nice in this regard, this way of thinking. So example example 2, he has a sub n is 2 to the n over n factorial. Now, what's n factorial? Probably should tell you about that, right? So this is something new for you guys, right? N factorial? You guys know what n factorial? Show of hands. Okay, about 2/3 of you have never, or don't remember factorial at least. So here's the definition. 0 factorial is 1. 1 factorial is 1. And then n factorial is equal to n times n minus 1 factorial for n greater than or equal to 1. And it's only defined for positive integers. So just to work out the next couple, what's 2 factorial equal to? It's equal to 2 times 1 factorial, which is just what? 2. What's 3 factorial? It's 3 times 2 factorial, which is 3 times 2. And then what's 4 factorial? 4 times 3 factorial by the definition, which, by the way, is 4 times 3 times 2. 5 factorial. That's 5 times 4 factorial, which is 5 times 4 times 3 times 2. You're starting to maybe see that there's another way we could state the formula for factorial. I've given you a recursive definition, right? But what's a kind of maybe perhaps a little bit sloppier, but indeed useful definition? This would be n times n minus 1, right? Times n minus 2, and then you just keep going until you get to what? 3 times 2 times 1. So this is another way of understanding factorial, but you got to remember how to interpret that formula in the case of 0 and 1, right? So 0 factorial 1, 1 factorial 1, 2 factorial 2, 3 factorial 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 720, 7 factorial is 5040. That's as far as I go. It gets really, really big, really, really fast. So having a factorial beats exponential is one of the things we'll learn in this course, all right? So my intuition when I look at this example is that will go to 0, all right? But at the moment, I just want to prove that this is in fact a decreasing sequence. So how can we do that? Look at an plus 1 over an is one way we could do it. I'm going to go through that way of thinking for a second here. What does that give us? 2 to the n plus 1 over n plus 1 factorial, right? Times what? N factorial over 2 to the n. So division is multiplication by the reciprocal, right? So I can divide by an, or I could multiply by 1 over an. 1 over an is n factorial over 2 to the n. Does this make sense to you guys, what I wrote? Okay, so then we do algebra or use the definition. N factorial is what? We have 2 to the n times 2, right? Times n factorial in the numerator. And downstairs, we've got n plus 1 times n factorial times 2 to the n. So some very nice cancellations happen here, right? The n factorials, they cancel. The 2 to the n's, they also cancel out. And we're just left with what? 2 over n plus 1. Yep.
I think I just got a little confused. So how did you get n plus 1 times n factorial? Can you just like move that out, or like on the denominator there?
Oh, that is the definition of, oh, did I say n plus 1? What do I mean? I'm an idiot. Oh, no. I mean, I am an idiot, but this is a separate issue. N plus 1 factorial. So you got to imagine putting n plus 1 in the place of n here. So that puts n plus 1 factorial, or let's say m factorial, is equal to m times m minus 1 factorial. But put m equal to n plus 1, what happens? So the recursive definition for the factorial, if I feed it n plus 1, it becomes n plus 1 times n factorial. So it's like replacing n with n plus 1 in the recursive definition is what I'm, is it? So that's why I replaced n plus 1 factorial with n plus 1 times n factorial, because of now, then the question is, what about n plus 1? If n is greater than or equal to 1, what can we say about this? Right? If n is greater than or equal to 1, that implies n plus 1 is greater than or equal to 2. Therefore, 2 over n plus 1 is what? The denominator is what? It is bigger than 2, right? Or if you like, you could just manipulate this, and this says 2 over n plus 1 is what? Right? I divide that inequality by n plus 1 to get me that. So however you see it, we have the a sub n plus 1 over a sub n is less than or equal to 1. So what's that say? That says we're in the star-star case, right? This is a decreasing sequence. It's a decreasing sequence. And what is, so, you know, a decreasing sequence has what? Has a sub 1 greater than or equal to a sub 2, greater than or equal to a sub 3, greater than or equal to a sub 4, greater than or equal to da-da-da, right? Decreasing sequence. So what does that say about, I mean, there's various things you can say here. By the way, with this example 2, suppose we're still talking about example 2 at the moment. Is there a lower bound? What's below any nth term in this sequence? Can you tell me? How about minus 1? Would minus 1 be smaller than anything in this sequence? I mean, I can actually write out some of them if it makes you feel less, you know, uncomfortable. What can you, I mean, you can see it. I said minus 1 just to try to provoke you to say what? 0, right. So these are all greater than, well, not equal to, these are just greater than 0, right? So this is in fact, this sequence, if we think about the range of the sequence, right, it's bounded. Would you agree? A lower bound would be 0. What's an upper bound? Yeah, 2 is an upper bound. In fact, it's the least upper bound, and it is the maximum of the range of the sequence. All right? He has his example 1. He looks at n over n plus 1, and he also finds that he comments on the upper and lower bounds for that one. Let me get to the, he has some more examples in here. Let's see here. Let me skip ahead a bit here. So we'll come back to properties of sequences shortly, but the punchline of all this is, so this way of thinking, all right, focusing on, is it increasing, is it decreasing, is there a least upper bound, is there, you know, a greatest lower bound, why do we care about this? Ultimately is the following theorem. the so-called bounded monotonic sequence theorem. All right, and here it is. This is theorem. I'm skipping ahead a bit just to kind of try to draw together the ideas here. This is theorem 11.3.6. This is on page 541 of the text. And it says the following. A non-decreasing sequence which is bounded above converges to blank a non-increasing sequence which is bounded below converges to blank. So what do you guys think goes in the blank? I'll add some more of its range. Of its range. In other words, the limit as n goes to infinity of a sub n is equal to the blank of the a sub n in case 2. I mean, let me call this case 1 and case 2. It's bounded below, it's non-increasing, which I think is more natural to think about as decreasing, right? It's decreasing. What does that mean? Anybody want to guess? Least upper bound, greatest lower bound. So this one, my example 2, right? My example 2 is decreasing, right? What's its greatest lower bound? If you think about it, it should be relatively apparent that it's 0, right? So by theorem, application of this theorem, the bounded monotonic sequence theorem, the limit as n goes to infinity of 2 to the n over n factorial is equal to 0. Now that wouldn't necessarily be how I would advocate arguing that, but it is a method we have to argue. Now there are problems where you really have no choice but to use the monotonic sequence theorem, all right? So I think there's a problem in your homework where I define a sequence recursively, all right? Like I define the nth and the n plus 1th to be connected by a certain rule. There's a recursively defined sequence. For a problem like that, if you can't actually find the formula for the sequence, you may have no recourse except to use the bounded monotonic sequence theorem. If you could